This is section 2.3 of your text and the last section in chapter 2 that we will cover. It's a short section and it's essentially a summary of what you know, which is fantastic. So this is Characterizations of Invertible Matrices. It is a fantastic theorem that does a great job of summarizing pretty much everything that you learned in chapter 1 and everything that you've learned in chapter 2. Specifically though for an n by n square matrix. So yes, when we worked on matrices in chapter 1 and some of chapter 2, they weren't always square, but those concepts that we learned all can be applied to these square matrices. And what the invertible matrix theorem says is that everything in this list is equivalent. What that means to you is if you can show, for instance, that A row reduces to the identity matrix, then you can say everything else on this list is also true about A. If you can find that A does not have n pivot positions, but in fact has fewer than n pivot positions, then you can say that everything else on this list is false. So everything that is listed here for the invertible matrix theorem, all of those statements are equivalent statements. A is invertible, A row reduces to the identity matrix, A has n pivot positions, the columns of A span Rn, Ax equals 0 has only the trivial solution, the transpose of A is an invertible matrix, the columns of A form a linearly independent set, the linear transformation that maps x to Ax is 1 to 1, the equation Ax equals b has at least one solution for each b in Rn. The linear transformation that maps x to Ax maps Rn to Rn. There is an n by n matrix C such that Ca equals the identity, and there is an n by n matrix D such that A times D is equal to the identity. All of these things mean the same thing. There's really not a whole lot of need for practice because really that last slide just summarized things that you already knew. So this is not anything new, but let's go ahead just for fun and do a couple of practice questions. So this first one says determine if A is invertible without actually finding the inverse. So if I had to find the inverse, I would write down A and then I would augment it, and to the right I would put the identity. They're saying don't bother, just do your row operations. So my first row is going to remain the same, and my second row I'm going to take -4 times my first row and add it to row 2. So -4 plus 4 is 0, -8 plus 5 is -3, and -12 plus 6 is -6. And then I'll do the same but with -7 times the first row, which gives me -7 plus 7 is 0, -14 plus 8 is -6, and -21 plus 9 is -12. Next thing I'm going to do is, of course, keep my first row the same. My second row and my third row, obviously I'm seeing what's happening already, but let's go ahead and finish. I'm going to take my second row times -1/3, and that's going to give me 1 and 2, so I've got my pivot here and pivot here. And when I take my second row times -2 to add to -3, I end up with zeros here. So what I have found is that I do not have a pivot in every row, so we cannot find A inverse since there is not a pivot in every row. And then that's of course by the invertible matrix theorem. As always, here's one for you to try, so press pause, try this question, then press play to see how you did. So again, I'm just going to take A. Since I don't need to find the inverse if it in fact exists, then I won't worry about doing the identity matrix on the right side. I'll just do my row operations. So first row will remain the same. second row, I'll take -3 times the first row and add it to the second row. So -3 plus 3 is 0, 0 plus 1 is 1, +6 plus -2 is +4. And then I'll take 5 times the first row and add it to the third row. So 5 plus 5 is 0, 0 plus -1 is -1, and 10 plus, make it times +5, so it would be -10 plus 9 is -1. Didn't want to mess that one up. Next, 1, 0, -2 is still looking pretty good. I've got that pivot here and pivot here, and obviously I want this guy to turn into a 0. So this guy is going to remain the same too, row 2. Row 3, I'm just going to add row 2 and row 3 together. So 0 plus 0 is 0, 1 plus -1 is 0, 4 plus -1 is 3. So I don't actually need to continue because it doesn't say row reduce and it doesn't say find A inverse. So what I know based on what I've done is there is a pivot in every row. So A is invertible since there is a pivot in every row. Done and done. Well done with chapter 2. On to bigger and better things.